Right now, like as you listen to this, ChatGPT is reading and generating just billions of words every single second.
Yeah, it's a completely mind-boggling scale.
It really is, but it doesn't read them like a book. It doesn't, scan left to right, line by line. It actually reads them in this massive four-dimensional mathematical space that would probably just make your head spin if you tried to draw it on a whiteboard.
Oh, absolutely. I mean, we tend to think of coding as these really neat sequential lines of logic, right? Like, if this happens, then do that.
Right, very rigid.
Exactly. But when you look under the hood of a modern AI, that rigid sequential logic is just, it's gone. It is replaced by this wild computational landscape of floating numbers, massive matrices, and these really complex geometric transformations.
And today, we're going to teach you the single string of code, literally just a handful of letters long, that makes all of that processing possible. So, welcome to the deep dive.
Glad to be here.
We're taking you on a journey into the actual mind and the raw mechanics of large language models. Our goal today, based on our sources, which are some really fascinating technical documentation and architectural breakdowns of PyTorch, is to look at how an AI organizes its thoughts using multidimensional tensors. And specifically, we are going to unlock the magic of this almost mythical PyTorch operation called Einsum.
Yeah, Einsum. It is the operation that completely changed how I think about programming, to be honest.
Really, just one operation.
Oh, yeah. Because when you step into the world of AI, particularly deep learning, you are no longer writing instructions for a machine to follow step by step. You are, in a way, defining the laws of physics for a universe of data. And Einsum is the engine that enforces those laws. It's really the beating heart of modern AI attention mechanisms.
Wow. Okay, so the mission for today is to demystify all this intimidating math and the arcane code that makes AI work. We want to take these abstract floating matrices and anchor them into intuitive physical concepts that you can actually picture in your head.
Right, because otherwise it's just numbers on a screen.
Exactly. So by the end of this deep dive, you are going to understand the secret of what's called declarative programming, which is what AI developers use to completely avoid writing endless, messy loops of code.
And it requires a fundamental shift in your perspective.
Yeah.
We are moving away from telling the computer how to do its job.
Which is how we normally code.
Right. And instead, we're learning to tell it exactly what we want the final reality to look like. It's a subtle difference, but it's everything.
Okay, let's unpack this. We can't just, start throwing lines of Python code around. We need to understand the physical environment where this data actually lives. So we are looking at how an AI physically stores data in its memory. And to do that, we have to start with the foundational container of all AI, which is the 4D tensor.
4D tensor, right.
Now, I know what a 3D tensor is, generally. Like, a single number is a dot, a list of numbers is a line, a spreadsheet is your basic 2D grid. So, a 3D tensor is just a Rubik's Cube of data.
That's a good way to picture it, yeah.
But the sources we are diving into today highlight a four-dimensional structure. The dimensions are batch, sequence, X, and Y. And I gotta be honest, I can't picture a 4D tesseract in my head.
No, I mean, very few people can visualize four spatial dimensions,
Yeah.
which is exactly why we have to map those dimensions to concepts we actually understand in the real world.
Yeah.
The tensor is really just a container.
Okay.
In standard language models, the data often flows in a 3D shape, right? You have batch, sequence, and then a single long list of numbers called the hidden size.
Right.
But keeping data in four dimensions, by splitting that hidden size into an X and a Y grid, it actually preserves crucial relationships that a flat 3D shape just destroys.
Okay, let's break down those four dimensions: batch, sequence, X, and Y, using a concrete scenario from our sources. Let's say we are building an AI translator, right, and the system is live on the internet. At the exact same millisecond, two different users hit the translate button on our app.
Okay, so that simultaneous action right there introduces our very first dimension, which is the batch. Batch is essentially the throughput capacity of your system.
Like how much it can handle at once?
Exactly. Because in traditional CPU programming, if two users hit a server, the CPU handles user A, finishes that, and then it handles user B. It's very sequential.
One at a time.
Right. But AI relies on GPU's graphics processing units. And those are designed with thousands of tiny little cores that desperately want to work at the exact same time.
Oh, I see.
So by grouping user A and user B into a quote-unquote batch of two, the GPU processes both requests simultaneously. The hardware literally demands this dimension to be efficient.
So the batch dimension is just the number of parallel realities the AI is tracking at once. We have a batch of two. Now, the second dimension is sequence. If user A types a sentence and user B types a sentence, the sequence is the context length, right? Like the actual number of words or tokens in those sentences.
Yes, exactly.
Let's say our system has a hard limit of 5 tokens per sentence. So our sequence dimension is exactly 5.
Which creates a really interesting architectural requirement. The GPU needs uniform shapes to do its math. It hates irregular sizes.
What do you mean?
Well, if user A types a 3-word sentence and user B types a 2-word sentence, the GPU can't just process a jagged, uneven batch of data. It requires a perfect rectangle.
Oh, I assume that's where padding comes in, right?
Yes, precisely.
Because if user A says, I love coding, which is 3 words, the system forces it to be 5 words so it can fit that sequence dimension. So it becomes, I love coding, pad, pad. The pad tokens just fill in the empty space.
They fill the space with mathematical zeros. That ensures the 4D tensor remains this perfect, rigid block of memory that the GPU can just slice through without hitting any blank spots or errors.
Okay, so we have batch, which is our 2 users, and sequence, which is a 5 words. Now we hit the tricky part, the X and Y dimensions. Because in a normal LLM, every word is turned into an ID card, like a long list of numbers representing its meaning. But in this 4D model, we don't use a single list, we use a grid.
Right, a 2D matrix.
We express the ID card of a single word as a tiny matrix, an X by Y grid. Let's say for our example, every word is represented by a tiny 2x2 matrix.
Yeah, so that 2x2 grid captures the embedded mathematical meaning of that specific word. The numbers inside that grid represent how that word relates to concepts like gender, emotion, time, or action.
So if we open up user A's data, the word I isn't just a letter anymore. It becomes a 2x2 matrix. Maybe the top row is 1, 0, and the bottom row is 0, 1. The word love is another matrix. Top row 1, 1, bottom row 0, 0. Coding gets its own matrix. And those 2 pad tokens at the end of the sequence, they're just 2x2 matrices filled entirely with zeros.
And happening in the exact same fraction of a second over in batch 2, user B's sentence, maybe they typed hello world, that gets its own set of 2x2 matrices for hello and world, followed by 3 of those zero-filled pad matrices. Every single word across every single user is now a uniform 2x2 grid.
That entire collection, like all those users, all those words, all those little grids sitting in the computer's VRAM together, that is our 4-dimensional tensor. But I'm still struggling to understand why we go through the hassle of keeping it in a 2x2 grid. I mean, if a word is just 4 numbers, why not flatten that grid into a simple straight list of 4 numbers? Just make it a 3D tensor, batch, sequence, and a list of 4. That seems so much easier to compute.
It does seem easier, and flattening data is incredibly common.
But
You have to understand what you destroy when you do it.
What do you mean?
Flattening destroys geometry. Think about vision language models, the AIs that actually look at photographs. In an image, the sequence dimension is the number of image patches. It's like taking a photograph and cutting it up into a grid of smaller squares.
Okay, sure.
The X and Y dimensions are the actual literal height and width, the pixel resolution of each individual square.
Oh, I see. So if I have a patch of an image that shows a person's eye, there's a spatial relationship there. The eyebrow pixel is physically above the pupil pixel. If I flatten that 2D patch into a single long 1D line of pixels, the eyebrow and the pupil might suddenly be like 50 numbers apart in the data. The AI just completely loses the concept of above and below.
You obliterate the spatial context. Keeping the data in 4D preserves the natural architecture of the information. And even in text models, where words don't have literal physical height and width, keeping the data in 4D is exactly how multi-head attention works.
Multi-head attention. Now that's the core of the transformer architecture, right?
It is. It's the mechanism where the AI figures out how every word relates to every other word in the sentence. By keeping the data in 4D, PyTorch, which is the framework these models are built in, can reshape the tensor into batch, number of heads, sequence length, and head dimension.
Right.
This allows the GPU to carve the tensor up and hand different attention heads off to different parts of the processor. So one head can look for grammar, another head can look for emotion, and they can do it entirely in parallel without their memory addresses crashing into each other.
Okay, to really help cement this in the listener's mind, I want to use an analogy from our sources. Forget the floating numbers and the tesseracts for a second. Imagine a physical stack of heavy office binders sitting on a desk.
That is a much better way to visualize the memory layout, actually.
Right, so the batch dimension is the number of binders in the stack. We have 2 binders on the desk, one for user A and one for user B. You open the first binder. The sequence dimension is the physical pages inside that binder. Our sequence is 5, so there are 5 pages in every single binder.
Okay, tracking.
Now look at one specific page. The X and Y dimensions represent a data table printed on that piece of paper. It has X rows and Y columns.
So when the computer wants to find a specific piece of data, it just uses an address, binder 1, page 2, row 1, column 2.
Exactly. It's just an incredibly strict filing system. And from what I understand, PyTorch operates on a batch-first logic. The outermost container, the first number you define, is always the batch of requests.
And that convention ensures that the memory is organized in a way that the hardware can ingest it as efficiently as possible.
So we have this massive filing system, binders full of pages, full of tables. Here is the massive problem, though. How does the AI actually cross-reference all this information? Like, if the AI needs to understand the sentence, the bank of the river, it needs to know that the word bank relates to river, not to a financial institution.
Right, context is everything.
It has to compare the table on page 2 with the table on page 5. Now, if I were writing a traditional Python script to do this, I'd have to write code to open every binder, turn every page, and check every row against every other row. I'd be writing for loops nested inside of for loops, like for binder in batch, for page in sequence, for row in X.
And anyone who has tried to write that kind of native Python code knows it is an absolute disaster. First of all, it's visually unreadable. You end up with this massive pyramid of indented code.
It's so ugly.
Second, it is highly prone to indexing bugs. An off-by-one error will crash the whole system. But most importantly, it is catastrophically slow. Python is an interpreted language, so running deep nested loops forces the CPU to evaluate the instructions one by one. It completely defeats the purpose of having a massively parallel GPU.
And that leads us to the absolute star of today's deep dive, the Supreme General Manager of AI Operations, a function called Einsum.
The Einstein Summation Convention. It is the tool that replaces all of those messy, slow loops.
Wait, Einstein, as in Albert Einstein, what does he have to do with PyTorch and large language models?
Oh, it's an amazing piece of scientific history. So back in 1916, Albert Einstein was formulating the general theory of relativity. He was working with Riemann curvature tensors, these massive mathematical structures used to describe how gravity bends four-dimensional spacetime.
Naturally.
Right. And to calculate these curves, he had to write out endless sprawling equations summing up all the different dimensions.
So he was basically doing what an AI does, but with a pencil and paper.
Exactly. And he was getting incredibly frustrated. Writing the summation symbol, the big Greek letter sigma, over and over again, keeping track of all the tiny little indices. It was exhausting, and it was prone to typos. So Einstein simply invented a shortcut.
He just made up a rule.
He did. She declared a new rule. If an index variable appears twice in a single term, we just automatically assume we are summing over it. We don't need to write the sigma symbol anymore. The convention itself dictates the operation.
That is wild. He was so annoyed by the math that he invented a shorthand that, a century later, is the foundational code for artificial intelligence.
He essentially invented a primitive form of declarative programming. He defined a syntactic rule where the structure of the symbols implies the action to be taken. And that is exactly what PyTorch's Einsum function does today.
Our sources make a really helpful comparison here. They say if standard matrix multiplication, like the torch.matmul function, is a specialized supervisor, then Einsum is the all-powerful general manager.
Standard matrix multiplication is very, very rigid. Torch.matmul expects your matrices to be in a very specific 2D alignment. If you hand it a 4D stack of binders, you usually have to write extra code to reshape the data, run the multiplication, and then reshape it back. It's tedious.
No, I see.
Einsum, on the other hand, doesn't care how deep the binders go. It just looks at the labels you provide and handles the entire operation internally.
Let's look at a piece of actual LLM code so you can picture this. This is the string of text that makes attention happen. It looks like this. Einsum, batch seq1 hidden, batch seq hidden, batch seq1 seq2, x, y.
Let's isolate the components of that instruction, because there's a lot there.
First, we have the variables at the very end, x and y. These are our input tensors. Think of them as two different stacks of binders. In AI terminology, X is often the query, which is what a word is looking for context-wise, and Y is the key, the information that other words contain.
And the text inside the quotes, that long string of words separated by commas and an arrow, that is the instruction manual. You are assigning arbitrary labels to the dimensions of your tensors.
So let's define the labels in that string. Batch is the number of sentences. Like our user A and user B, seq1 is the length of our query sequence. seq2 is the length of our key sequence.
No.
And hidden is the size of that ID card, the embedding dimension.
Right. So when the code says batch seq1 hidden, it is explicitly telling the Einsum engine, look at TensorX. Its first dimension is the batch, its second dimension is the query sequence, and its third dimension is the hidden state. It establishes the physical reality of the data.
Okay, I think the abstract labels are getting a bit heavy. Let's ground this with the student grades analogy from our sources, because I feel like this perfectly illustrates how the math actually resolves. Let's step away from AI tokens for just a second.
Sure.
Imagine a single classroom. In that class, there are two students. They're taking three subjects. And the teacher has three different weights for those subjects because, math is more important than gym class.
A classic weighted average problem.
Right, so we have two tensors. Tensor X is the student grades. Its shape is two students by three subjects. It's a 2 by 3 matrix. Let's put real numbers to it. Student A gets a 90 in math, an 80 in science, and a 70 in gym. Student B gets a 60 in math, a 90 in science, and a 95 in gym.
Got it. And tensor Y is the weights. Its shape is just one-dimensional. 3 weights. Say math has a weight of 2, science is 1, and gym is 0.5.
If you want to calculate the final score for each student, you need to multiply student A's math grade by the math weight, science by science, gym by gym, and then add those three numbers together to get one final score for student A. Then do it all again for student B. Now, with Einsum, you don't write loops for that. You just write Einsum, IJ, JI, X, Y.
Let's decode how the engine interprets JHI. First, it looks at tensor X. You labeled it IJ, or is the student dimension, J the subject dimension. Then it looks at tensor Y, the weights. You labeled it J.
And this is the critical part, right? The engine sees J in both inputs. It sees J as the subject in tensor X and J as the weight in tensor Y. What does it do?
It acts on Einstein's convention. Because J appears in both input tensors, the engine automatically aligns those dimensions. It takes the three subjects and locks them against the three weights. It multiplies 90 by 2, 80 by 1, and 70 by 0.5.
Okay, so it does the multiplication perfectly, but what about the addition? How does it know to add those three results together to get the final score?
Look at the right side of the arrow, the target output shape. It just says I.
The J is gone.
Exactly. The J is completely missing on the right. So the engine logic dictates, the programmer didn't ask for J in the final output. Therefore, I must collapse the J dimension. It takes those multiplied numbers, 180 for math, 80 for science, 35 for gym, and sums them together. 180 plus 80 plus 35 is 295. Student A's final score is 295. The J dimension vanishes, leaving only I.
And I is the students. So the output is just a list of the two final scores for the two students, like 295, 257.5. It perfectly calculates the weighted total score per student in one tiny string of characters. It truly is a matching game of letters.
It is an incredibly elegant abstraction. It turns complex linear algebra into simple pattern recognition.
Okay, I want to test this logic, though. Let's try to break the rules. What if I label a dimension I in my first tensor, and I happen to know it has 10 elements, and I label a dimension I in my second tensor, but that one only has 8 elements? I tell the engine to match I with I. Does Einsum just match the first 8 and ignore the leftover 2?
No. If you do that, PyTorch will immediately throw a runtime error and crash your program. You have violated what's known as the dimension consistency constraint.
Why does it crash? Why can't it just be smart and trim the excess?
Because Einsum is just an interface. Under the hood, PyTorch is dropping down into highly optimized C++ code to allocate physical memory in the GPU. If you use the same letter I, you are making a binding mathematical contract with the compiler. Those dimensions occupy the exact same spatial footprint. If one is 10 and the other is 8, the C++ backend doesn't know how to allocate the memory array. It refuses to guess your intentions. I must equal I, period.
So the letters dictate the memory footprint. That makes sense. I like to picture Einsum as an automatic factory sorting machine. You tell it what labels are on the input boxes coming down the conveyor belt. That's the left side of the arrow. You tell it what labels you want on the finished product going out the door. That's the right side. And the machine automatically unpacks the boxes, multiplies the contents if the labels match, adds them together if a label is missing from the final order, and repackages everything perfectly. You never have to write the code for the robotic arms moving the boxes.
That analogy perfectly captures the essence of declarative programming. You declare the desired state of reality, and the back-end engine constructs the operational mechanics to achieve it.
But wait, if the right side of the arrow dictates the shape of the finished product, what if we play with the order of those letters? Say we have our student grades again, but we don't multiply by weights. We just have a 2 by 3 matrix of grades. I is students, J is subjects. The standard output would be IJ, AIJ. But what if we change the instruction string to IJ? We just swap the I and the J on the right side.
You've just performed a matrix transpose. You flip the table.
So the matrix goes from being 2 students by 3 subjects to 3 subjects by 2 students. The rows become columns, and the columns become rows.
Correct. The data is fundamentally reoriented.
Here's my question about that. How does PyTorch actually handle that in the hardware? If I have a massive LLM with billions of parameters and I transpose a giant matrix, does the computer physically pick up every single number in the RAM, copy it, and move it to a new physical location to create the transposed columns? Because if it does, that physical copying of data would bring the entire system to a grinding halt.
You've hit on one of the fundamental bottlenecks of early computing. Moving data in memory is incredibly expensive, computationally speaking. It's much slower than doing the actual math. So PyTorch is something incredibly clever. It does not physically move the data. It creates a view.
A view, like a window.
Think about how computer memory actually works. RAM isn't a 2D grid. It's a single, massive, one-dimensional tape of memory addresses. When you create a 2x3 matrix, PyTorch stores those 6 numbers sequentially on that tape. To read it as a 2x3 grid, PyTorch calculates an index called a stride. It says read 3 numbers, then jump to a new row, read 3 numbers, jump to a new row.
Okay, so the stride is just the rule for how to read the 1D tape as a 2D grid.
Exactly. So when you write ISIG, PyTorch doesn't touch the numbers on the tape. It simply recalculates the stride. It changes the rules of how it reads the tape. It calculates the index addresses on the fly to grab the numbers in the new transposed order.
That is brilliant. Einsum acts like a smart GPS. It doesn't physically pick up the buildings and move them around to create a new route. The data stays exactly where it is. It just calculates a non-standard route to visit those addresses in a different order. It's a logical alignment, not a physical transpose.
And that saves gigabytes of memory bandwidth and crucial milliseconds of processing time during model training.
Okay, so manipulating the right side is safe and efficient. But I'm going to propose another bad idea. What if I want to transpose the data, but instead of changing the right side, I change the left side? I write GIA, J-I-G, and just swap the input labels. Does that work?
I would strongly advise against that.
Yeah.
If you change the left side incorrectly, you are essentially lying to the GPS about where the buildings are physically located.
How so?
Well, the left side of the Einsum string defines the structural reality of your tensor as it currently exists in memory. If your matrix is physically stored as 2 rows and 3 columns, and you label it G, you are telling PyTorch that the first dimension, the rows, has a size of J, which is 3, and the second dimension has a size of I, which is 2. You are claiming the matrix is 3 by 2 before any operation even happens.
Oh, I see. When PyTorch goes to read the type, it expects the first dimension to be size 3, but the physical tensor only has a size of 2. It hits a wall.
Exactly. The memory addresses won't match the strides. The contract is broken. The golden rule of Einsum is the left side defines reality, the right side defines your desire. Never lie about reality.
Let's move deeper into the math. We've seen how Einsum handles transposing and how it handles summing data by dropping a letter, but what dictates the type of multiplication it performs? Because there are 2 very different ways to multiply matrices, and Einsum can do both with just a 1-letter difference.
Right, this is the difference between element-wise multiplication and true matrix multiplication. Or, as the sources beautifully put it, the difference between a zipper and a loom.
A zipper and a loom. Let's look at the expressions. Expression 1, J-I-J-K-G. Expression 2, G-J-I-J-H-A-J. The only difference is that final letter on the right. Let's unpack the first one. Matrix X is G, matrix Y is I-A-J, and the output is G.
So, analyze the letters based on the rules we established. We have J and I on the left, we have J and I on the right. Are there any letters missing on the right?
No. All the letters survived, which means, according to our rules, no summation happens, no addition.
Spot on. Because no dimensions are collapsed, this is purely an element-wise multiplication, also known mathematically as the Hadamard product. Because we paired G with IR, it aligns matrix X with the transpose of matrix Y, and then it simply multiplies the points that overlap. It's a one-to-one relationship.
And that's why it's called a zipper. The teeth of a zipper only interlock point to point. Left tooth number 5 only interacts with right tooth number 5. Row 1, column 2 of the first matrix only multiplies with row 1, column 2 of the second matrix.
Exactly. It's a highly localized operation. But now, look at the second expression. G, I-I-G-J-I-J.
The I has disappeared on the right side.
Which triggers what action?
It must sum over I. It has to collapse that dimension through addition.
Right. This is standard matrix multiplication. And the computational cost of this operation is drastically different from the zipper. The sources refer to this as the combination explosion.
Explain the combination explosion. Why does dropping 1 letter suddenly make the computer work so much harder?
In the zipper scenario, but the base, the engine knows exactly which 2 single numbers to multiply to fill a specific coordinate in the output. It's a direct mapping. But in JJ, the output matrix is a grid of J by J. It doesn't have an I coordinate to anchor it. To resolve the missing I, the engine is forced to calculate every single row of the first matrix against every single column of the second matrix.
Ah, so it has to calculate the Cartesian product.
Yes, if j is 1,000 and I is 500, a zipper operation performs exactly 500,000 multiplications.
Mhm.
But a full matrix multiplication requires the system to weave every row across every column. The number of operations explodes exponentially.
And that's the loom analogy. You aren't just matching points. You are weaving every horizontal thread with every vertical thread to create a full, dense fabric of mathematical relationships. Every number touches every other number. I can see why that would heat up a GPU.
Oh, it is the single most computationally expensive part of running an LLM. Weaving the full fabric is necessary for self-attention, where every word needs to mathematically look at every other word to understand the context of the sentence.
But what if we don't need the whole fabric? What if we are running an operation where we only care about very specific relationships and calculating the whole loom is a waste of time and electricity? Let's say we only want to look at the main diagonal line running down the center of the matrix.
This is where Einsum elevates from a convenient shorthand to a masterclass in algorithmic efficiency. It's the art of restriction.
Okay, let's look at the expression I, G, Nash I.
So we have matrix M labeled IJ and matrix N labeled G. This is the exact setup for a standard matrix multiplication loom. But look at the output string. Just I.
It's a one-dimensional vector. We drop the J, so we know it's doing the matrix multiplication weaving, but we also drop the second I. Compare that to a full multiplication, which would be IJJ2, outputting the full 2D matrix. By asking for just I, why does the math become so restricted?
It all comes down to output seats. By requesting -I, you are providing only a single, one-dimensional row of seats for the results to land in. You have created a constraint anchor.
Walk me through the mechanics of that constraint. How does it work?
If you ask for matrix 2, the output is a 2D grid. The engine has the freedom to say, okay, I'll multiply row 1 of matrix M with column 2 of matrix N, and I will place the result in seat coordinate, 1, 2. The seat exists, so the calculation happens. But in IJG, there is no seat when there is only seat 1, seat 2, seat 3.
Because it's just a straight line.
Exactly. So when the engine calculates the result for seat 1, Einsum forces row 1 of matrix M to multiply only with column 1 of matrix N. It literally turns off the combination explosion because there is
Courses IT boy everywhere. It calculates only the main diagonal of the matrix product and ignores the rest of the fabric. That is surgically precise.
And the real-world implications of this are staggering, particularly in a technique called contrastive loss.
Contrastive loss. Let's dig into that. What is it, and why does this diagonal trick matter?
Think about how Apple's Face ID works, or how you can open Google Photos and type, "my dog at the beach." The AI has to understand that an image of a dog matches the text, dog. To train this, engineers use contrastive loss. They feed the AI a massive batch of samples, say 10,000 images and 10,000 text descriptions.
Right.
The goal is to maximize the mathematical similarity between an image and its correct text description, the positive pair, while pushing away all the incorrect descriptions, the negative pairs.
So image 1 needs to match text 1, image 2 needs to match text 2.
Exactly. Now, if you use standard matrix multiplication, the loon, the GPU, would calculate a 10,000 by 10,000 grid of similarity scores. It would calculate the score for image 1 against text 1, but it would also calculate image 1 against text 2, text 3, all the way to 10,000. That is 100 million calculations.
Yeah.
And if you have a batch size in the millions, you run out of memory instantly.
But wait, the correct matches image 1 to text 1, image 2 to text 2. They naturally fall on the exact center diagonal line of that massive grid.
That intuition is spot on. We often only care about calculating the loss for the correct pairs. We just want the diagonal. By using Einsum, IGI, you instruct the GPU to only calculate the 10,000 diagonal pairs. You completely bypass the other 99 million useless calculations.
That's incredible.
You save massive amounts of VRAM, you save processing time, and at the scale of a company like Google or OpenAI, you literally save millions of dollars in electricity and compute costs.
That is mind-blowing. One missing letter in a line of code translates to saving millions of dollars of compute. But I have to play devil's advocate here. What if my specific algorithm needs the other diagonal, the secondary diagonal that runs from the bottom left of the matrix to the top right? Can Einsum surgically extract that?
Here we reach the boundary of Einsum's power. It cannot extract the secondary diagonal.
Wait, really? Why not? It seems so omnipotent.
Because Einsum is fundamentally a pattern matching engine based on index equality. It can only enforce that I must equal I. To extract the main diagonal, you just say row 1 equals column 1. But to get the secondary diagonal in an n by n matrix, the relationship requires arithmetic. You need the row index plus the column index to equal the total size minus 1. I plus j equals n1.
Ah, and Einsum doesn't do addition and subtraction on its labels.
It strictly matches labels. It has no mechanism to perform algebraic equations on the coordinates themselves.
So how do AI engineers get around that limitation?
You step outside of Einsum, use a separate PyTorch function, like torch.flip, to physically reverse the matrix left to right in memory. That action rotates the secondary diagonal into the position of the main diagonal, and then you can run Einsum to extract it.
Okay, that makes sense. So to summarize this section, the output string on the right side of the arrow isn't just a label for the final product. It is a literal physical constraint on the math engine. The number of letters you put on the right side dictates the combinatorial freedom the engine is allowed to use.
It defines the boundaries of the universe the math is allowed to happen in.
We've seen Einsum manage two tensors beautifully. It can zip, weave, and slice diagonals. But the true superpower of this general manager is that it isn't limited to just two inputs, it scales.
It scales incredibly well. You can pass it a single tensor or you can pass it half a dozen.
Let's look at the single tensor first. If I just write Einsum IM, what happens?
You've given it one matrix. You labeled the rows I and the columns I. Because the labels are identical, it forces the engine to only look at elements where the row coordinate equals the column coordinate. It extracts the main diagonal of a single matrix without doing any multiplication.
What if I drop the I on the right side entirely? Einsum, Einam, nothing on the right side.
The I disappears, which dictates summation. It extracts the diagonal numbers and then adds them all together. In linear algebra, calculating the sum of the main diagonal is called finding the trace of a matrix.
And what if I have a normal matrix ID and I write Einsum, Iam, Ina?
The j dimension disappears. It collapses the columns. So it calculates the sum of every single row in the matrix, returning a 1D vector of row totals.
It's just so versatile. It replaces torch.diagonal, torch.trace, and torch.sum, all with one unified syntax. But it gets even crazier. It can chain 3, 4, or more tensors at once.
This multi-tensor chaining is where Einsum becomes absolutely indispensable for the architecture of large language models.
Let's look at the expression IJJK KL Desal. 3 tensors.
This expression is calculating matrix A times matrix B times matrix C, all in one continuous operation.
Let's trace the alignment. The J links matrix A and matrix B. The K links matrix B and matrix C. And the I and L are the only letters that survive to the right side, forming the final output dimensions. Where is this massive triple multiplication actually used?
It's used right at the climax of the transformer attention mechanism. After an AI calculates how much attention every word should pay to every other word, it generates a matrix of attention scores. It then has to multiply those scores by a matrix called the values, and then immediately multiply that result by a matrix of projection weights to finalize the output.
If I were writing that normally, I'd say intermediate matrix.matmul scores, values, and then I'd say final output, you just torch.matmul intermediate matrix weights.
And doing that would be highly inefficient. That intermediate matrix you just created, it has to be physically allocated in the GPU's VRAM. For a model with billions of parameters, that temporary matrix is massive. It eats up your memory bandwidth, and the moment the next line of code runs, that temporary matrix is discarded. It's a waste of resources.
But with Einsum...
With Einsum, you pass all 3 tensors in one line. It looks like this. BHSS, BHSD, 80s BHS out.
Whoa, hold on. You just threw 4 dimensions and 3 matrices at me? Let's rewind and translate that slowly. We have batch, head, sequence, that's the attention scores matrix.
Right.
Then we multiply by batch, head, sequence, dimension. That's the values matrix.
Exactly.
And we multiply by dimension, output. That's the projection weights matrix. And the output is BHS out. So the second S, the sequence context, and the dimension, they just vanish. It weaves and sums them all together, leaving batch, head, sequence, output.
Exactly. And because you declared the entire operation at once, PyTorch's backend can look at the whole equation before it starts doing math. It evaluates the sizes of the dimensions and automatically finds the most optimal contract path. It figures out the mathematically most efficient order to multiply those matrices without ever fully instantiating that massive memory-hogging temporary matrix in VRAM. It keeps the intermediate steps in the ultra-fast cache of the processor.
That is insane. It's a level of optimization you could never achieve with standard loops. Okay, I have one ultimate challenge from the source text to see if I truly grasp this. What does this expression do? I. 4 separate tensors, all labeled I, and absolutely nothing on the right side of the arrow.
Think through the rules. We have four 1D vectors. They all share the label I, so they are perfectly aligned point to point. It takes the first element of vector A, multiplies it by the first element of vector B, times the first element of C, times the first element of D.
Okay.
It does this element-wise multiplication down the entire length of the vectors. And because there's no letter on the right side, it sums every single one of those resulting products together. The output is a single solitary scalar number.
Mind blown. Okay, one final challenge from the text. I want you to walk me through this. How do I get the sum of squares for each row of a matrix using Einsum? Let me try to logic this out.
Go for it.
If I want the sum of squares, I need to square the numbers in the matrix. That means multiplying the matrix by itself, element by element.
Correct. What is the label setup for element-wise multiplication?
I take matrix M and label it IJ. I take matrix M again and label it IJ. So my input is IJ, IJ. That gives me the Hadamard product, squaring every number in place. Now, I want the sum of each row. A row is I, the columns are J. If I want to sum the row, I have to collapse the columns. I have to drop the J.
So what is your final string?
Einsum, IJ, IJ, M, M.
You've got it perfectly.
Yeah.
You take M, square it point by point, and collapse the horizontal columns into a sum, leaving only a vertical vector of row totals.
It is so incredibly powerful. Instead of writing 4 clumsy lines of code where I call dot transpose, then dot reshape, then dot matmul, and finally dot sum, creating temporary data at every step, I just write one elegant string. It's like giving the AI a treasure map instead of turn-by-turn directions. You just mark the X, and the engine evaluates the terrain and finds the absolute best path to get there.
And that brings us to the core philosophical shift we've been circling this entire deep dive. Understanding tools like Einsum is the bridge between just writing code and truly thinking in high-dimensional linear algebra.
It's not just a syntax trick, it's a completely different mindset.
It is the essence of declarative programming. In traditional imperative programming, you are a micromanager. You tell the computer exactly how to do everything. Loop through I, loop through J, fetch this memory address, multiply this, add that to an accumulator variable. It's exhausting, and the computer is constrained by your human limitations in algorithmic design.
Yeah, that makes sense.
With Einsum, you step back.
Yeah.
You become the architect. You declare the end state, the exact dimensional relationship you want the data to have, and you let the highly optimized C++ backend engine figure out the how.
We started today trying to understand the physical reality of AI memory. We went from understanding those massive stacks of binders, the 4D tensor with batch, sequence, X, and Y, down to the magical string of letters in Einsum that can zip those binders together, weave their pages into complex fabrics, transpose their tables, and compress gigabytes of data with pinpoint accuracy.
And by stripping away the intimidating for loops and the rigid matrix multiplication functions, we are able to see the pure geometric logic of how an AI processes language. We see the math.
To wrap this up, I want to leave you, the listener, with a provocative thought to mull over. Think about the last time you had to manually wrestle with data rows and columns, whether you were trying to write code for a database or even just fighting with a giant Excel spreadsheet, trying to VLOOKUP and sum across a dozen tabs. If you could write a simple 5-letter code to instantly define how every single cell relates to every other cell across 5 different sheets, how would that change the speed at which you solve problems? Next time you see a massively complex system, whether it's an AI model or a global supply chain, don't get lost in the steps. Ask yourself, what are the underlying letters trying to align?
It ultimately all comes down to finding the right alignment.
It really does. Thank you for joining us on this massive deep dive into the muddy, magical waters of AI mathematics. Keep questioning the mechanics behind the magic, and we'll see you next time.
Until next time.